So we had started entropy, and I think it was the same board. Okay, somewhere over here. So we had started entropy, and just a quick recap of what we were doing, what we were up to. I told you that entropy is a measure of a disorder of a system. So I gave you the example of an untidy room and a neat and tidy room, a high entropy state, and you have a low entropy state. Uh, and whenever something happens, whenever there's a process, whenever there's anything happening, whether it's related to chemistry or whether it's not related to chemistry, there is a change of entropy. Things move from low entropy to high entropy state, and from high entropy to low entropy state. So the change in entropy is delta S, and it could be positive, and that means the entropy or disorder is increasing, and it could be negative. And I told you that high entropy states are kind of more stable. Uh, Low entropy states or the orderly states are kind of unstable. I explained why that systems, they like to go towards higher entropy. They like a more stable state. So it's easier to go into a high entropy state. And then we talked about how to figure out the sign of delta S, and I told you that you can uh, figure that out by looking at the change of state. So solid to liquid to gas, that's an increase in disorder. And I also explained that when temperature increases for a substance, the disorder jumps most of the time, especially when there's a state change. Otherwise, the entropy doesn't really increase a lot. And so 5 centigrade, water at 5 centigrade, water at 60 centigrade, the entropy or disorder is kind of exactly the same, not much different. Second, we discussed that if the number of moles of gas increase, then there's going to be more disorder. If solid changes to liquid or aqueous, that's also an increase in disorder. So we talked about that, and we also talked about why delta S was important. I told you that whenever you have any chemical reaction, two things happen. Either heat is produced, like you burn a match and there's a fire and heat is produced, burn paper, there's heat produced, or when that particular chemical reaction happens, there's a very large delta S, a very large change in entropy, either decreasing or increasing. So I told you that the mechanical work that is produced, or the useful work that is produced, is more related to delta S. Most of the time, the heat that is produced or given off or taken in, that's kind of not very relevant. And I gave you an example of how cars run. I told you that cars don't run on the heat that is produced when octane or petrol burns, which is completely useless. Cars run because when an octane molecule burns, all of a sudden it produces a lot of gas molecules, and those gas molecules, there's a lot of disorder created, and which is why they're going to produce work. And I showed you the example of how steam engines work. I mean, that's an endothermic process, unlike burning petrol, but the concept is the same. There's a large increase in disorder, and which is why there's going to be so delta S is positive. That's we like delta S positive. And I explained to you this thing. I told you that when you give a system energy, two things happen: either the temperature increases, or you have the energy is being used to break bonds. And when the bonds are broken, that's when the entropy increases. So I told you that entropy change is basically the useful work that is produced at a specific temperature by the system. So, for example, if you take oxygen gas and you take it at a specific temperature, it's going to move the piston a bit, and whatever useful work that it's able to create, that would be its work done uh, at a specific temperature. So the unit for entropy, which we haven't written over here, it's the unit for entropy is joules per Kelvin per mole. So that's your unit for entropy. So previous, is this all clear? You have the concept, right? Is this clear to everyone?
Yes.
Yes.
So moving on. And I told you about this. I just rewrote the expression. I told you that the work that's done due to entropy change, that's minus T times delta S. Okay, so we talked about that as well. Now, the second type of question is that you'll be asked to measure or calculate. You'll be asked to calculate delta S. And what you'd be given is provided with entropy values of reactants as well as products. So they would give you a table and they would tell you, let's say oxygen is being used. So they'll tell you that oxygen gas has an entropy value of whatever that value is at room temperature. So you'll be given the provided with entropy values of reactants as well as products. So the formula is very simple. Like every reaction, you have a reaction that's happening, reactants turning into products, and you have the entropy. Let's say you have the entropy values of the reactants, and you have the entropy value of the products. So what is the change in entropy? The change in entropy is going to be the delta S is going to be the entropies of the products minus the entropies of the reactants. So that is what your formula will be. It's going to be products minus your reactants. So that's a simple formula. You want to find entropy change, just find out the difference between the product's entropy and the reactant's entropy. So is this formula clear?
Yes.
Yep.
So it's a simple formula. So we're going to do a couple of questions. Let me just open some past paper questions. 1 second. So let's try and do a few questions. We're going to use product minus reactants, and we're going to find entropy values. Let's do the more straightforward ones first. Just 1 second. So this one, for example, this one, you can see over here that in this question, you're already given the entropies of the products, which is MgO, so that's provided, and you're also given the entropies of Mg as well as O2. And remember, entropies are per mole, so if it's half mole, you would have to multiply it by half. So I'm going to do if I want to calculate the entropy change of this particular reaction, I'm going to find the entropies of the products and subtract it with the entropies of the reactants. So the expression, be careful with the sign, the expression is going to be products. The products is MgO, so that's 26.9. And I'm going to subtract it with the reactants, which are Mg. So there's 1 Mg, that's one of the reactants. So that's 32.7. And the other reactant is O2. So that's half into O2's entropy, which is 205. So can somebody do the calculation and tell me what the answer is? What are we getting? And be careful with the signs and with these calculations. It's 26.9. Ethan, Mohammed, are you done with this? 32.7.
Yeah, I got
negative 108.1.
Negative what?
108.1.
108.1. Okay. I'm not sure. Is everyone else getting this?
I got 0.3.
I got 0.3 too.
Okay, I mean, that's the only difference, right?
Yep.
So it's negative 108.3. And be very careful about the units as well. This is joules per Kelvin per mole. The only thing is it's not kilojoules. I mean, you're used to writing kilojoules, you're used to writing because enthalpy change, bond energies, etc. All those values were in kilojoules. I mean, whenever you see enthalpy change, it's written in kilojoules. You can see it over here as well. So always remember that entropy is in joules. It's not in kilojoules. So even if you're doing this quickly, just be very careful. Don't write kilojoules as a unit. It's joules. Entropy, the unit is joules. I say anyway. So this is how you're going to find entropy change delta S. And I said one other thing is it's negative, right? So let's go back. Why is it negative? It's decreasing. So why do you think it's negative? Why is disorder decreasing?
Because it's an exothermic reaction.
The entropy has nothing to do with delta H.
Forms a solid.
Yeah, it's turning into a solid, so that means there's less disorder. It was a gas previously. There was oxygen gas, so there was a lot of disorder. Now it's turning into a solid. So the disorder is decreasing. ठीक है, Ibrar, is this clear?
जी sir. Sir, for the units of delta S, is it per mole or is it just mole?
Sorry, it's per mole -1. ठीक है, so it's per mole, but it's written over here. It's per mole. ठीक है. So next is make sure don't make that mistake. Then you have let's do another question. Again, you're being asked to find the entropy change of this reaction, so it's going to be products minus reactant. So try and quickly do that. Product is NH3, and there are two of them, so it's going to be 2 times 193. Take this one, and minus the reactant, so it's N2. So that's plus 192, and 3 H2s, so that's 3 times 131. So what is the delta S in this case?
Negative 199.
Negative 199 joules per mole per Kelvin. So that's your entropy change. Again, it's negative. So why is it negative over here? It's gases turning into gases. Why is it negative?
Because of the moles of gases on each side. But previously there were 4 moles.
So there was more gas. Now there's less gas. So the disorder would decrease. So that's and remember. So it could be the other way around as well. I mean, it's a simple question. So we can do another question, which is, where's the other question? Let's try and do this one. So sometimes what would happen is that it's the same formula, but the delta S this time is already given. So we know that delta S is what? Products minus reactants, right? So it's products minus reactants. Now, in this particular case, your delta S would be, its value is already given. It's minus 225.7. And you have your products, which are SiCl4. And the entropy of SiCl4 is also given. That's 239. So that's my product. And I'm going to subtract my reactants, which are silicon. So the entropy change, this one. Just hold on 1 second. Let me just. Just hold on 1 second. Can you try and find okay, that's fine. I said so the reactants, silicon is given, that's 18.7, right? What is not given is they're asking for the entropy of Cl2. That's not given. So let's take that as x. So it's going to be 2 times x. Try and find what x is. So it could be the other way around. Can anyone quickly try and find?
Negative 223.
As it's coming out to be negative 223. Joules per cal.
Yeah, I'm also getting the same answer.
Okay. So it's negative 223, and why is it negative? Because gas moles are decreasing, or anyway. So you can get the question both ways. You can either be asked to find the delta S, or using that delta S, you can be asked to find the entropy of a substance. So it could be both ways. So that's formula. So this formula is clear, right? Is it clear to everyone?
Yep.
Yes, sir.
So now the next thing we're going to do is that's probably the last thing. That's so you're going to be asked to calculate delta S. Just be careful about moles. You have to multiply by moles as well. So that's one formula. Now the last formula that you're going to do is it's going to be this one, which is known as Gibbs free energy. Yeah, that's your last formula. And that's your delta G. If there's a knot, that's a standard Gibbs free energy. That means it's calculated under room conditions, 25 degrees centigrade and 1 atmosphere pressure. So what is Gibbs free energy? It's the total energy available to a system. So it's the total energy that's available. If it's negative, that means it's exothermic. That means the system is going to produce work, right? I mean, we know that whenever energy is negative, that means work is being produced. Similarly, delta G could be positive, and that means overall the system is endothermic. And that means system needs energy or work. And we can write that here as well. Okay, so you've got Gibbs free energy. That's a concept that whenever something is happening, like there's a car running, right? So is the system producing work or is it consuming work? Does it need energy or is it releasing energy? And that's the total. And we're talking about the total energy because they're all forms of energy. A system is going to produce, like if you burn a match, energy would be produced in many different forms. So it's the total energy that's available. And if it's negative, that means the system doesn't really need any energy. That means that the reaction is feasible, or whatever that's happening is feasible and it's spontaneous. It doesn't need your help. It doesn't need any external help because it is producing work. And if overall the system requires energy, that means it's not feasible. I mean, if you don't give it energy, it's not going to work. It's not feasible and it's not spontaneous. So that's the idea. So whenever you have any process, it's going to have a Gibbs free energy. That's the total energy that's available to a system. Now, going back, we already talked about Gibbs free energy. For example, this car running on fuel, right? Mainly, there are two ways a system is going to produce energy. One of them is the heat energy that's going to produce, and the other one is the work that it's going to produce due to entropy change. Okay, so it's going to release a lot of heat energy, or it's going to consume a lot of heat energy. Either the temperature is going to increase or it's going to decrease. And the same with entropy. Either work would be produced or it would be taken in. I mean, if disorder decreases, the piston would be the one that would be doing the work. It would be coming down. So either work would be produced or it would be consumed. So I'm going to write over here that delta G is the sum of both forms of energy, mainly these two energies. Delta G is basically the energy that is released. It's the heat energy that is released or absorbed. So that's basically your delta H. And plus it's the work that is produced or consumed due to entropy change because of the disorder. So you have your entropy change work as well. And that could be positive or negative as well. And we did calculate this. I told you that, I told you about this formula. I told you that if you want to figure out the work that's done due to entropy change at a specific temperature, the formula is T times delta S. It's minus T times delta S. So this one is minus T times delta S. Is this expression clear?
Yes.
Do you guess this clear to everyone?
Yes, sir.
Okay. So that's your delta G. We can write this in the form of an equation, which is that delta G is going to be delta H. Sorry, delta H. That's the heat energy that's released or consumed, and plus minus T delta S. So the plus would be gone. And remember why we added a negative sign over there, because if delta S is positive, the work done would be exothermic. So which is why you need a negative sign over there. So that's your expression. And the other thing about this expression is that delta G is in kilojoules per mole. Delta H, the same thing. It's in kilojoules per mole. And delta S is in joules per mole per Kelvin. The Kelvin part would get cancelled out because you're multiplying it with temperature. So the temperature has to be in kelvins. Remember, the temperature always has to be in kelvins. And the Kelvin part would get cancelled out so the unit would pretty much be the same except for this joules part. So either convert everything to kilojoules or either convert everything to joules. If you're trying to find delta G or delta H, you convert everything to kilojoules. If you're trying to find entropy change using this formula, then convert everything to joules. Is this clear, this formula?
Yep.
Yes.
Okay, so remember this formula. You can use this formula in two ways. One question would be that you would be actually asked to use these input values. Like you have the enthalpy change of a reaction, you are given temperature, and you have the entropy. You just measured entropy change, so you have entropy change as well. So you put in these values, you got delta G, and you're going to figure out that if it's negative, that means that the system is kind of feasible. It's spontaneous. It doesn't need your help. If it comes out to be positive, that means it requires energy, and you don't give it energy, it's not going to work. So it's not feasible, and it's not going to be spontaneous. So that's one way. So there's going to be a quantitative question, plus there's going to be a qualitative question. For example, one thing I just told you, remember this inequality, which is when is a reaction feasible? A reaction is going to be feasible if delta G is negative. That means it comes out to be less than 0. That's when the reaction is feasible. So that means, what is delta G? Delta G should come out to be negative, then the reaction is feasible or spontaneous. So delta G is delta H minus T delta S. So that means delta H minus T delta S must be less than 0. So remember this inequality. You're going to use this. They're going to ask you about when is the reaction feasible. So you try and solve this inequality. If they're asking for temperature, at what temperature is the reaction feasible? You solve this inequality. Is this inequality clear?
Yep.
Yes.
And vice versa, the opposite. What if they're asking when is the reaction not feasible? So if you want the reaction to be not feasible, the delta G must be greater than 0. And what is delta G? That's delta H minus T delta S. So that should be greater than 0 as well. So that would indicate that the reaction is not really feasible. And there are only a few things that are actually changing, and that's one of them is temperature. Temperature is a variable. So reactions, the feasibility of reactions is going to differ at different temperatures. So I'm just going to do one question qualitatively, and I'm going to talk about this. I'm going to take a simple reaction, and we're going to try and solve for this. There's a reaction that's happening, H2O liquid turning into H2O gas. Now, reactions are not feasible all the time. There are certain conditions and certain temperatures at which reactions are feasible. Can you tell me exactly when is this reaction feasible? At what temperatures is this reaction feasible?
100 degrees.
And any temperature that's above 100, right? And below 100, this reaction is not feasible. And it's going to become even less feasible as you go to a lower temperature. Like at minus 150, this reaction would pretty much, it's not going to happen. So you get the idea, right? That temperature is a factor about when you talk about feasibility of a reaction. Is this clear?
Yep.
Achha, so the same one, I'm going to use Gibbs free energy now. I mean, we know what this reaction is. We know that it is feasible at higher temperatures, right? Like let's say at 1000 degrees centigrade, this reaction is really feasible. It's going to happen very, very quickly, and it's going to be very spontaneous. At 100, it would be barely feasible. Like it would happen, but boiling would take some time. At 90, it's not going to happen. You go down, it would just become not feasible. If you keep going up, the feasibility would keep on increasing and the spontaneity keeps on increasing. It becomes really spontaneous. At 2000 degrees centigrade, this reaction would be, if you throw water on hot iron and this reaction happens abruptly, very spontaneously. So I'm going to use Gibbs free energy to figure this out. Who's going to tell me what is the sign of delta H over here? Like,
Negative.
Is boiling exothermic or endothermic?
No.
Endo.
Okay, so boiling is endo. It requires energy to actually make the molecules energetic. So that's endothermic, right? Can you spot the sign of delta S? What's the sign of delta S?
Negative.
Positive. Positive.
Positive. That's positive because there's disorder increasing. There's a gas being formed. Is this clear?
Yes.
Achha, so now I'm going to use and justify this thing. We know it's feasible at higher temperatures, okay? But we're trying to figure out, and we're going to come to the same conclusion using Gibbs free energy. So we know Gibbs free energy is delta G equal to delta H minus T delta S. Now this reaction is endothermic. So delta H has a positive value. It's an endothermic reaction, right? And we know that delta S is also positive. So if delta S is positive, that means this entire expression has a negative sign next to it. So that means this expression is actually, it's going to have a negative value. Is this clear?
Yes.
Okay, so one of the terms, now delta G is the sum of two terms. One of them is positive and the other term comes out to be negative. Because delta S was positive and it has a negative sign attached to it. So overall, it's going to come out to be negative. So if I want to make this reaction spontaneous, I need to, how do I make delta G more negative? I want delta G to be negative, right? I want it to be negative. So delta G is the sum of two things. one is positive and the other one is negative. So the negative part should be larger, right? Is this clear?
Yes.
Okay, because delta G is the sum of one thing that's positive and the other thing that's negative. So if overall I want delta G to be negative, the negative part must be larger. So if I want to make the negative part larger, so what should be the value of T? Should it be big or small?
Big.
Okay, so the reaction is feasible at higher temperatures when the value of T is larger. Is this clear to everyone?
Yep.
Yes.
Okay, so we reached the same conclusion, but we use the Gibbs free energy expression and the equation, and we use that to get over here. So there would be all sorts of reactions, and there would be all sorts of reactions. Some would have enthalpy changes that are positive, and some would have enthalpy changes that are negative. Delta S would be positive, delta S would be negative. So I'm just going to do one more. Let's try and where's the car engine? The petrol burning, right? Let's say burning petrol and doing all of this, right? At what temperatures would it be more feasible or less feasible? I mean, should I do it at a lower temperature? Should I do it at a higher temperature? Does it have a specific temperature or not? And is it feasible at all temperatures or not? So this reaction, where were you? Just 1 second. So let's talk about this one. And we're going to come to the steam engine question as well. So can you tell me what is the sign of delta H? Is it an exothermic reaction or, I mean,
Negative.
so
Exothermic.
it's an exothermic, it's negative, right? And what's the sign of delta S? Is disorder being created when petrol burns?
G, positive.
So that's positive. So overall, I want delta G to be negative. So delta G is basically delta H minus T times delta S. So this time what's going to happen is that delta H is negative and delta S is positive, right? So since it has a negative value in front of it, so this term would also be negative. Now what's happening is that the first term is negative and the second term is also coming out to be negative. So that means delta G is going to be always negative. I mean, there is no possibility that it's going to turn positive. So that indicates that this reaction is always feasible, no matter what the temperature is. Is this clear?
Yes.
And it's going to be even more feasible if you keep a bigger temperature. Like if you keep a bigger value of temperature, the negative term becomes bigger. And this one is also negative. So, I mean, overall, it's going to become even more negative. So that means the reaction would become even more feasible. It's always feasible at all temperatures. And it's going to be even more feasible at higher temperatures. So is this clear as well? Is this clear? Ethan, is this clear?
Yes.
Ibrar, Zaib, Zabi, is this clear?
Yes, yes, sir.
Okay, so let's do some questions later on, in the next class then. But just remember this. You're going to get 2 questions on this. One of them would be simple, that you'll just plug in the values and you'll find the value of delta G. The other one would be a qualitative question. I mean, even in those plugging values thing, make sure you remember this inequality, that if they're asking to make the reaction feasible and asking for the temperature or anything that's specific, you just make this inequality that this thing should be less than 0. And the other thing would be this qualitative question, that they might just ask you, well, what temperature should you use, higher or lower? So let's continue with this tomorrow then. Okay, everyone.
Chalala.
Allah Hafiz, sir.
Take care, Allah Hafiz.
Sir,
Yes?
for the delta G, right? Does it
Yeah.
it depends only on delta H, right?
On both things.
Because temperature cannot be negative, right?
Yeah, temperature is in Kelvin, so it can't be negative.
So it will always be negative. The negative
Nee,
G
delta.
S.
No, but delta S could have a different sign.
Oh, all right. Yes.
So this
Understood.
thing could be positive and negative, and this thing could also be positive and negative. So it depends on both. Okay.
Yes. All right. Yes.
Oh, okay then. Take care.
Thank you.
Thank you.